Hello, welcome to Waka Breaking It Down. This is the introductory kind of feedback quiz, but kind of lesson for inference with slope. It's chapter 26 in our AP Stats book, and in the book, there's only one chapter that covers inference dealing with slope. So this is it. Um, we're almost done with the year. This is like second to the last. We're going to do chapter 5 after this with matrices and stuff, but or with chi-squared, which is matrices a lot. But here we go, slope. So working with slope when you're doing inference. Since we're doing inference, I'm going to go back to the big boss sheet. You should have one of these. You can get one from the unit plan if you don't have it. And this is where we did all our different inferences, right? We did two mean and one mean and proportions and intervals and all the tests, right? Chi-square we haven't got to yet. That's the very last thing this year. But we're doing slope. So you can do a t interval for slope. And this is the same t that we use for means, for small sample sizes with means, but it's a t interval, but for slope. And you can also do a t test for slope. Um, let's get to the feedback quiz, and then this stuff will come out of it. Okay, so on the first question, what are the four conditions you need? When you're doing scatter plots and you want to do inference, you always want to make sure you have a linear model. And it has to be a good fitting linear model. The problems that we talked about last unit with scatter plots is that maybe it was curve data, maybe you had fanning going on, maybe you had an outlier, something like that, right? That would cause a problem. So the conditions basically go through all those and just say, hey, do you have a good linear model so that we can use this inference? If I look at the big boss sheet, you'll see they kind of list them out over here on the right, over here, right? All these. We try to say that our data is independent of each other and random. That would be really nice. But at the very least, you just want to make sure it's representative of the population. Like whatever data you're dealing with, you're like, okay, even though it wasn't totally random, at least I know these are the same type of people, the same type of things in the overall population that I'm interested in. All right, so we got to check the scatter plots and the residual plots. Does it fan? Do we have any outliers? Or does it look linear? Is it like a nice, evenly scattered distribution? Right? And then the last thing is the histogram of the residuals. Um, you're supposed to make sure your residuals are nice, unimodal, and symmetric. There's a really good reason for that. We're going to be doing predictions. Let me see if I can kind of put it over here on the side real quick. And it kind of goes along with the fanning, really. Basically, the fanning is what I'm looking at. Um, if you have a scatter plot that's nice and even, right? Sorry, I'm kind of writing on the right here. And you do your model. If you have the residuals in the middle, kind of up and down, are the same distance away as at the end, and over here and everywhere you look, if that distance is pretty consistent, then inference is going to work for any particular x value. Because remember, we can do predictions for any x value. So what if it wasn't? What if I had some fanning on the right over here, right? And the points in the middle or towards the end were not as spread out. Well, the problem with this is that if I make a prediction on the left, I'm going to have less variation that I'm supposed to be reporting in my confidence interval than if I make a prediction on the right. I have a lot more variation. And when I try to do my confidence interval, neither one of these are going to be correct, probably, right? So we are using the same standard error for all the predictions. So we want that residuals, the distance away from my model, to be very consistent. The formula for the standard error is right down here. Hope you can see that down here, right? So that is the same no matter where you're at on your graph. So you have to have that nice consistency along the way. Technically speaking, whoops, wrong button. When you have a regression model, it's kind of like you're doing these little vertical normal curves everywhere. When you make a prediction, if I make a prediction over here, I've got a little normal curve over here. If I make a prediction here, I've got a normal curve that's going to match that prediction. And we want all those little normal curves to be the same shape. We don't want one to be bigger than the other because we want to use the same standard error for every single one of those normal curves. All right, so that's why the kind of like checking the residuals to make sure they're consistent. So I listed it out here maybe a little more wordy. So we want it to be random and independent, or at least representative of our population. That's at a very minimum. The data should be linear, not curved, right? We want to check that residual plot and make sure it's not curved. I did a quick stupid little graph here with x's and y's. Just made up some data, and if I were to do analyze and show my residual plot, then I could see that, okay, this is pretty scattered. It's like below and above and below and above and below, right? So that's scattered. There's no pattern. This is just as high as these. It would be nice if I had more data points, but there's nothing wrong with this data set here, right? Okay. So no fanning. You got to check that. That's a third condition. So it's not curved. There's no fanning. There's no outliers, right? And we have consistent things. So you can check the residuals like a histogram or a box plot of the residuals or the XY direction and see if you have any outliers. It's pretty rare that they would ask you to actually calculate the outliers. I mean, it's possible, I guess, or maybe they ask you a question about it, kind of, but it's pretty rare they'd ask you to calculate it. You just need to be able to look at plots and see if, oh, there's an outlier here, there's an outlier there, or at least it looks like there is, right? You can always do some quick calculations too. Like a lot of times, I'm going to jump to number 2 and use this data, but a lot of times they give you the standard error of the residuals, the standard deviation of the residuals. So you can kind of, like in the residual direction, you can think to yourself like, okay, I mean, 0 is always the center of my residuals. So if I go up two of those standard errors and 2 of those down, like 5 up and 5 down, I shouldn't have any residuals that are bigger or smaller than that. That kind of idea, right? Okie doke. Just check your residuals usually. All right, on to number 2. So in the following equation, so here's our equation for standard error. You'll see that shows up when you're doing confidence interval. That's the equation you want. And it has pieces. It has the standard deviation of the residuals. It's got your sample size in it. And it's got the standard deviation in the x. So we need to, like, why are those part of the standard error? Like, why are those important? But you see, those are needed to make your confidence interval. And then when I go down to do a test, that same standard error is being used on the bottom to do your t-value, to get your t-value out of it. Okay, so it's really important that we understand this standard error. All right, so let's look at the pieces. That's what this question is all about. Like, break down the pieces. What do they mean, right? Why are they there? So we have the standard deviation of the errors on top. Obviously, the more spread out your data is, then the more error you're going to have. So this is directly right on top for a direct correlation there, direct association. Like, as S goes bigger, as your residuals get bigger, your error is going to be bigger, right? You just have more variation going on in your scatter plot. In this case, it's 2.59. You can see it was given to us right there. All right. Why is S of X in there? Now, this is very interesting. You could have a bunch of data points that kind of look like they're clumped up, right? And you're not quite sure if the slope should go like that or if it should go up like that. And it's really hard to see. But if those exact same y values, if I took these y values for each of those points, but I changed the x values and spread them out more, so like if this point would maybe stay there, but this point might I'll keep the same y value but slide it over a little bit, and then these I'll slide them out, and these I'll slide them out. And if I start to spread out the x values a little bit more, right? So same y values for these points, but maybe spread out more. It's going to be easier to see where the slope is. And when you do the mathematics, it actually makes your slope I don't know, like you're more confident in your slope. So this is on the bottom of the equation because it'll decrease the error. The further out your x's are spread, right? That's the standard deviation in the x direction. So the more they're spread out in the x direction, the less the standard error is going to be. You're going to be more confident about your slope. Okay, and then the last one, oh, sorry, there's a calculation here to actually solve for s of x because they didn't give that to us. So I knew the standard error. If you look up here, the standard error is 0.008. We haven't really used this before, right? So this is new now in our computer readouts and stuff. So that value goes in there. I have my S from here, and I have N from here. So I could calculate that. I just did it on a calculator page, and you can see up here I did a solve. I got 68.7 when I solved that. Okay, so that's where the 68.7 is coming from. All right, so then the last piece of this is N. Now you can see N's on the bottom it's on the denominator. So the equation is saying that as N gets larger, I'm going to have less error. Well, hopefully that makes sense to you. Like the more data points you have, let me do a quick little thing. If I have like three data points, then I'm like, is this supposed to go like this, or is it supposed to go like this? It's really hard to tell. But the more data points I start throwing in there for you, right, then you're like, oh, okay, I see. This is supposed to go like that, right? So it really starts to lock in your slope the more data points you have. So your standard error will go down. So that's the reason this is built the way it is. It's like, okay, have low variation. Like if you want to have a low standard error, you want to have low variation, you want to have your x's spread out, and you want to have a large sample size in order to reduce your error, right? So that's what all that's kind of explaining of why that equation is the way it is. Okay, part B, calculate a 95% confidence interval for the slope. So the degrees of freedom is 2 less than the n. Oops. So in this case, it's 20 because we started out with 22 data points. They told us that, right? Up here, n is 22. The t value I have to get on my calculator. So all you need to do is get the degrees of freedom, and then you can go do it. So you'll see here I used inverse t, and we want 95% confidence, so I use 0.975. Remember, we have to add in one of the tails, and then my degrees of freedom, which is 20 in this case. So I get 2.086 basically for my t value. So that just goes in my confidence interval. I already know the standard error that was given to us at the top. So it's nice because this is given to you a lot, right? So I can just write that out quickly. I don't have to use the confidence interval on the calculator or anything. In fact, it would probably be impossible because you need a scatter plot for that. You can't do it unless you have x and y values. So you just have to write it by hand. Go ahead and calculate the plus and minus for that, and you'll get your boundaries, right? So if I were to interpret that, where'd my interpretation go? It's not there. It says interpret. I didn't interpret it. So we are 95% confident that the true slope now, right? This is the slope between, sorry, I forgot what we were talking about. Time for a zip line and the length of the zip line. Between the length of the zip line, I'm just thinking right now, I'm going to change this. The zip line and time to ride is between 0.188 and 0.222 seconds. Sorry, this is slope, so it's seconds over, so it's seconds divided by meters, right? So it's slope. I was just thinking there's probably a better way to describe the slope, talking about the increase of 1. So I am going to reword this. So I'm going to say we're 95% confident that the true slope, or let me reword. So we're 95% confident that for every one increase in the zip line length, the time to ride that zip line is expected to rise by 0.11 to 0.22 seconds. So for every increase of 1 meter, right? So that for every one increase in the length of the zip line, 1 meter increase, sorry. Just see, this is what you got to think about, right? Units and all that. In the length of the zip line, the time to ride in seconds is predicted to increase by about 0.11 and there we go. There we go. So I got the whole idea of what a slope is, right? For every one in the x direction, and then then the increase in the y direction, and the units are all in there. That's the right way to do that, to say that. Okay, remember we're doing inference for slope. Now, why is that important? Maybe I should mention that real briefly. Slope is so important because if you had a slope of 0, that would mean you don't have an association between those two variables. Like, they're not related to each other, which is the whole point of what we're trying to figure out in regression. Are these two variables associated to each other? Is there a connection? So if you have a slope that's not 0, then you can prove, you can show that, oh, there really is an association. Sometimes it's positive, sometimes it's negative, but as long as it's not 0, then there is an association going on. So this next problem is a test, and that's kind of getting at the heart of that. Okay, so we're taking vitamin D in women, and we're checking the estrogen levels. I actually looked this up. There was an article that said something about women taking vitamin D, and that it would help them kind of establish their estrogen levels better. So anyway, that's something that's real. So what is the degrees of freedom for the test? Well, we have 24 data points, so 24 minus 2 is 22. Why do we minus 2? Mr. Waka? Well, that's because we have two variables. We have an x variable and a y variable. So there's more room for error, if you will, in each direction. So we have to account for that by lowering the degrees of freedom. When you lower the degrees of freedom, you're introducing more error into your inference. So you're just allowing for that flexibility of all the different variation going on in two directions, right? Okay, what's our null and alternative? Like I said, we want to establish that there is no association to begin with. So we make our slope equal to 0. Notice I'm using a capital B. That's for the true slope of the whole population, which we're never going to know, but that's what we're trying to infer. All right, so the null hypothesis is that there is no association between vitamin D intake and estrogen levels. So the alternative, we're trying to show that there really is uh, a correlation or an association going on. So we want to see, is there a positive association? Is the slope change? Okay, so you don't have to do the test in this case, but in the future you will. They say, well, you do the test and the p-value comes out to 0.037. This is less than 5%, right? So what are you concluding? If it's less than 5%, we reject the null hypothesis, just like we did before, and we have evidence to suggest. Remember, the evidence is talking about the alternative. You do not talk about whether the null is true or not. You just either reject it or fail to reject it. In this case, we rejected it and say we do have evidence to support the alternative, which is that the increase in vitamin D intake will change the estrogen levels, right? We'll have an increase in estrogen levels. All right, so we do have an association between those two variables. The slope is not 0, right? At least that's what our evidence says. Okay, number 4, we got a whole bunch of data. You might want to pause here. You're going to have to put all this data into your if you haven't done it yet, right? Put your data into a spreadsheet. So I put class and AP exam scores in my spreadsheet. Okay. Once I have all that, we're going to do a prediction for 3.2. We want a 95% confidence interval for that. Okay, so I'm going to go to here and I'm just going to go to confidence intervals. And you'll see at the bottom here, it says linear regression T intervals. That would be for the slope as well as for the predictions, the response. So you have a choice. Do you want to do a confidence interval for slope, or do you want to make predictions? So I put response in for a prediction. I say, okay, what's the X list? Well, that's my class score. What's the Y list? That's the AP exam score. And then we're predicting for 3.2. So I have to write in here 3.2 is where I'm predicting, and a 95% confidence level. Okay, enter it in and you get all this stuff. If I go to the top of this, you'll see my point estimate is a 4.03. That's an AP exam score. So if I have a 3.2 grade in AP stats, then I'm expected to get a 4 on the AP exam, right? That's 14 degrees of freedom. Now I have two intervals showing here, right? There's one here, and then there's another one down here. So which one am I using? Well, it depends on if they're talking about an individual person or if you want the average. So when I got to go back and just look at this, this says a score of a student. So it's not the average of all students with a 3.2. It's just the score of a student with a score of 3.2 in the class. So I'm looking for the interval that's actually larger for the individual. So this one you can see is more spread out. There's more variation with one person than there is for an average of a whole bunch of people. We've learned that in the past. So this interval is if I were to look at the average of all the students that have 3.2 in the class, what would their GPA on average be, right? Or not, what would their AP exam score be on average, right? This is for an individual person who has a score in the class of 3.2. I'm 95% confident that their AP exam score will be somewhere between 3.5 and 4.6. So about a 4. It's possible they get a 3. It's possible they get a 5. But most likely they'll get a 4. Right? So that says that right here at the bottom, right? So that's it. That's the introductory lesson and feedback quiz to chapter 26, Inference for Slope.